Hello, hello, hello. Am I audible? All right. Welcome to week 4 problem solving session. I am your instructor, Sachin, a PhD student in the Indian Institute of Science. And as usual, we'll solve 10 problems related to the topics covered in this week's lectures and then we leave. Okay, this week we studied convolutional codes. Let's start with the first question. My habit is that unless it's necessary, I won't write down the options so that you don't become too reliant on options all the time. Okay, first question. Which of the following statements is false? Well, for this, I have to give you the options. First statement is convolutional codes have typically a small value of n and k. That is a true statement. You should have seen examples in the class where you might take just one bit in your code sequence. Uh, yeah, your k might just be only one. Yeah, your n might just be two. So we saw examples like that. Whereas in a typical linear block code, like a Hamming code, you had 4 codes, so k and n were 4 and 7, which is much larger. And you might have even larger codes. Like we saw in a few of the questions last week, we had Hamming codes of 63 and 57, something like that. But in conventional codes, you can have k and n to be 1, 2 smaller values. So that's a true statement. Second statement is maximum likelihood decoding complexity of convolutional codes increases exponentially with increase in constraint length of the code. This is also a true statement. If you saw in the last lecture, Viterbi decoding algorithm, there was a trellis and you had to decode. There were different paths. So if your constraint length is higher, you'll have a larger shift registers. That would mean there are more states. So a larger number of states would mean that there are more possible paths for the trellis. The trellis would be bigger. And yeah, uh, a small increase. Say if you have one more shift register, if you have only two memory elements, then you would have four states. But if you had three memory elements, you would have eight states. That's a doubling. So the number of states would increase as 2 power x would be if you are dealing with binary where there are x memory elements. So that's an exponential function. So and your constraint length will depend on uh, the shift register length. So when you do maximum likelihood decoding, the complexity will keep increasing with the increase in constraint length. So that's also a true statement. And C convolutional codes can be implemented using shift registers. This is also true. We saw several examples in the class. So the final option must be false. We'll check that anyway. The memory order M of a convolutional code has no effect on the free distance of the code. This is obviously a false statement. So the answer is option D. So when we are trying to find the free distance, you saw in lecture, we will try to find the function t of x and the power of the smallest x term will be your free distance. So if you have more and more shift registers, then you will have larger and larger state diagrams, and the paths, forward paths, will increase. So the numerator in that t of x will have higher and higher order x power of x terms. So the free distance actually does depend on the memory order M. So that statement is a false statement. Okay, that's question number 1. We'll go to question 2. Question 2 says, let C be a convolutional code with generator matrix G of D is the following matrix: 1 0 1 plus D square plus D cube and 1 plus D 1 plus d cube, and d 1 plus d square and 1. That is the convolution generator matrix of the convolution code. Its equivalent generator matrix is, and again we have options here. First one 1 1 1 1 0 1 plus d d1. Second one is 1d 1 plus d 0 0 1 plus d d1. Is this your assignment for? This is a previous year assignment actually. They're not supposed to overlap. Uh, that's a problem then. Let me check what this year's assignment is. I'll see if other questions are also the same or if they're different. Okay. Okay, this is the same assignment. I guess I gave you the answers to the first question then. Well, there will be marks for this, right? So some people will be writing the exam. If you're not writing the exam, then it's fine. But if you're writing the exam, the people who didn't attend might complain. It was easy for you, but it might not be easy for other people. So we don't know what level of students are coming. There might be students who find it hard, who might not be able to get all the right answers. Give me a minute or two, I'll think about what to do. I guess we'll just continue. I guess we'll continue. I won't tell you the answers explicitly, I'll just give you the method. Maybe I'll change some of the things and try with that. But then the answers might not come out nicely. Okay, option C was what is it? C is both A and B, and D is none of the above. There are two ways you can try to solve this. First method would be you take your original matrix, and both the methods are the same, but the way you do it is different. That's all. It's a normal linear algebra where you try to get the options from this matrix by doing row operations. So you could try. So the row operations you're allowed to do are same as in your linear algebra courses. So you can add a row to another row. You can exchange rows, and you can add a multiple of a row with another row, but the multiplier should be a power of d. So it doesn't make sense. There's only Yeah, it's a D or 1 or 0. So that those are the only options. Because this is mod 2 arithmetic, the only numbers you have are 0 and 1. And since we are dealing with this operator D, we are also allowed to multiply by D. So you could try something like okay, this is just one step. So if I do this step, then we'll get the answer directly. So how about I change some of this, some of the terms in this matrix. Let me see. Let me use a matrix from a different question where they haven't asked you to find the. Okay, let me just change the question, and instead of dealing with this matrix, we'll try this some other matrix. I will change the question to, instead of checking answers, I'll ask you to give an equivalent generator matrix. So let's try a few examples. A generator matrices as given. Given equivalent generator matrix to each of them. Okay. We'll try the generator matrices from the last problem, question 10. So that would be, one of them would be the first one, 1d square d10. So let's say, okay, you can do any number of row operations, and as long as it's a different matrix and you get it through row operations, then it will be an equivalent matrix. So let's, instead of doing random row operations, let's just try to bring this to the row echelon form. So to do that, what we would do in linear algebra, you would have to get rid of this d. So how can you get rid of that d? So in modular arithmetic, if mod 2 arithmetic, if you add a number to itself, that will give you a 0. So 1 plus 1 is a 0 and 0 plus 0 is a 0. So regardless of what d is, we'll take d plus d to also be 0. So you can do the following row operation. Row 2 will be changed to row 2 plus d times row 1. So d plus d, first row will remain the same, second row will change from d plus d will give you a 0, then d square multiplied by d is d cube, get 1 plus d cube and d square. Now uh, this would be an equivalent generator matrix. Right, let's try another example. So if you have a matrix like this, 0 1 d, d square d, 1 plus d, so you can do row exchanges. So row 1 goes to row 2 and row 2 goes to row 1. So this will be equivalent to d square d1 plus d 0 1 and d. You can further divide by, uh, let it be as it is. Okay, you can divide row 1 by d. So row 1 will become row 1 by, or d square, sorry. So then the first term will become a 1, this will become a 1 over d, this will become a 1 plus d over d square, 0 1 d. So that will be an equivalent generator matrix. So if we want to check, let's try to see if, okay, another method where you want to check if two generator matrices are equal. From the lecture you would see that g of d and g prime of d are equivalent if there is an invertible matrix T of D such that J prime of D is equal to T of D G of D. So let's say I want to check whether these two matrices in option A and B that I've given, whether they are equivalent. So that would mean 1 D square D D10 is some matrix should be invertible times 01 D square D 1 plus D. So in the assignment question, it is not too hard to follow this. You can find simple row operations that will reduce your given generator matrix to one of the options. But these two matrices here, they are not similar, and it's not obvious what you would do to check if these two are equivalent. So in such type of situations, you can use this. So you'll assume T of D to be some arbitrary matrix filled with variables. And what should be the dimension of T of D that you'll check. So this is a 2 by 3 matrix and this is a 2 by 3 matrix. T of D should be invertible, so it's a square matrix, so this should be a 2 by 2 matrix. Let's call this A, B, C, D. And we'll do the multiplication. So A times 0 is 0, so this element will be BD square. This will be A plus BD. This will be AD plus B plus BD. This will be D square, C plus DD, and CD plus D plus DD. You'll do this and then you'll equate each element on the left to the element on the right. So if these two matrices are equal, that would mean that 1 is equal to BD square, should imply B is 1 over D square, and D square is equal to D, which should imply that D is 1 over D, and then C plus D is 1, but small d is 1 over capital D, so C plus 1 over D into D is 1, which will imply C plus 1 is 1, which means C is 0. So if C is 0, I'll substitute it right away to make this matrix simpler. So this is BD square DD square A plus BD. I'll keep the rest of the things the same. This will reduce to DD and this will reduce to D plus DD. Now finally we have D plus DD should be equal to 0. What would that mean? I'm comparing these two elements. So that would mean that but small d is equal to 1 over D from here. So let's check that. 1 over D plus D times 1 over D is equal to 0. 1 over D plus 1 is equal to 0, which means 1 over d is equal to 1. But okay, this it doesn't make any sense. So this thing 1 over d is not equal to 1. So this is a contradiction. So that would mean that there is no matrix T of D such that G prime of D is equal to will become T of D into G of D, which would mean that G prime of D and G of D are not equivalent, right? So you can, for your assignment question number 2, if you can find out the row operation that you need to reduce it to the options, that will be fine. Suppose you aren't able to guess what row operations you should do, or if you are not sure if you can even get the options in the first place by doing row operations, then you can follow this method which I showed you. So equate whichever two matrices you want to check the equivalency of. So you write one of the matrix as a product of this T of D and the other matrix, and then multiply. So you can take these A, B, C, D as your variables, multiply the right hand side, you will get equations. So two matrices are equal if and only if each of the entries are equal. So one by one the entries you check, and if those two are really equal, then all the equations will match. So you will get bd square is equal to 1, you will get a plus bd is equal to bd square. So all those equations will have a solution. If they are not equivalent, then some contradiction like this will show up. Okay, you can try whichever, you can do whichever method is easier to you. All right, that is your second question. Now we'll go to question 3. Yes, we will get recordings. You'll have to you'll have to go to your course page, right? And there will be some section for problem solving recordings. Not sure, let me check. Yeah, there is. So if you go to your course page, right, there is a course outline to the left. There you will get your lecture videos, week 0, week 1 up to now. They have released week 5 lecture videos. Below that, at the bottom, there is one section called problem solving session July 2024, and there's a link there you will have to click, where you'll get an Excel sheet, and that Excel sheet contains uh, a presentation folder link and a YouTube link. So the lecture videos will be, you can click on the YouTube link for each of the lectures and you'll find these problem solving sessions. So there is another TA, I'm not sure what problems he's solving. He might be solving different problems. So you can check his videos also. And these Lecture slides will also be there, so you can revise it. All right, we'll go to question 3. Give me 1 minute, I'll be back. Okay, I'm back. Consider a rate 1/4. I'll keep it as 1/4 convolutional encoder with input output relationship given by, and I'll change the input output relationships. I'll give you different input output relationships, and you can follow the same procedure for the assignment question. Only thing is you'll get different answers, but the method will be the same. Let's see. Let's do ul plus ul minus 3. ul2 is ul plus ul minus 3 plus ul minus 3 plus ul minus 4. VL3 is ul plus ul minus 1 plus ul minus 2. VL4 is ul plus, let's keep this one the same. Okay, maybe not. Alright, so I slightly changed the equations from your assignment problem. Alright, now the question is, what is what are the generator sequences of the code? So for each of the outputs there will be a generator sequence. Since there are 4 outputs, there will be 4 generator sequences. Also, you can see that each of the output sequences depends on ul minus 1 up to ul minus 4. So ul will be the input at time l, and you're storing ul minus 1, ul minus 2, ul minus 3, and ul minus 4. So there are 4 memory elements. So this we solve it by inspection. So the answer, your output sequence, the ith output sequence will be the sum of the convolution of u, and it will be the convolution of u and j, which is nothing but the following sum of ul minus j gji, where your gi is the generator sequence, which will be a vector. So this j will give you the index. So your generator sequence will be, the ith generator sequence will be gi, which will be equal to g1i, g2i, etc. up to gli, right? So here j goes from 0 to m, m is 4. So j will go from 0 to 4 in our case. And j is equal to 0, what will you get? You will get, right, let's expand this out and see. For j is equal to 0, you will get ul g0i. J is equal to 1, you will get ul minus 1 g1i, etc. up to ul minus m gmi, right? So your generator sequence g is, the ith generator sequence is nothing but these coefficients g0i, g1i to gmi. So you compare this equation with each of your equations given here. So the coefficient of ul will be g0. For the first one, it will be g01, right? So let's do that. And for that, here you can see that j goes from 0 to m, which is 4 here, so it'll go from 0 to 4. So if we write each of our input output sequences containing u of l minus k terms, where k goes from 0 to m, it will be simpler. You can just read the generator sequence from the equation itself. So vl1, it has ul and ul minus 3. You can write it as ul plus 0 times ul minus 1 plus 0 times ul minus. Of course, you can do it directly, but you might make small mistakes if you write it directly. So you can write it out like this: ul minus 4. That would mean that your g1 is nothing but, write the coefficients of each of these terms as a vector. So 1 0 0 1 0. So that's the generator sequence for your first code word output, first output. And we'll do the same for all other outputs. VL2, it has only L minus 3 and L minus 4. So the first 3 will be 0 and the last 2 will be 1. So the second generator sequence is 0 0 0 1 1. Then the third equation, you have L minus 1 and L minus 2. So a 1 in the first three positions and a 0 in the last two positions. So G3 is 1 1 1 0 0. Finally, the fourth generator sequence, fourth output equation has UL L minus 2 and L minus 4. It has UL, doesn't have L minus 1, it has UL minus 2, no UL minus 3, it has UL minus 4. So the fourth generator sequence is 1 0 1 0 1. So the set of generator sequences will be 1 0 0 1 0, right? Second one will be 0 0 0 1 1. Third one is 1 1 1 0 0. Finally 1 0 1 0 1. So you can use the exact same procedure for your assignment question. Rewrite your equations in this way and directly write down the coefficients. Okay, that is your question 3. Question 4. The time domain generator matrix G of the code given in question 3 is what? So we'll write it down without any options. For that, first we should know what the generator sequences are. G1, G2, G3, G4. Let's copy that down from the previous question. 1 0 0 1 0, 0 0 0 1 1, 1 1 0 0, finally 1 0 1 0 1. Now your generator matrix in terms of these generator sequences will be G0, G1, G2, G3, G4. The next row it will be staggered. You will get G0, G1, G2, G3, G4. Next staggered once more. And this will continue this pattern. Rest of the place there's a 0. You can leave it blank or you can put circles like this. Different mathematicians use different notation. Okay, so one more thing you have to note is this G0 is not the same as any of your G1 where the 1 is a superscript. So this G0 will be the 0th element of each of your generator sequences put in a vector form. So this G0 will be G0 of the first generator sequence, G0 of the second, G0 of the third, G0 of the fourth generator sequence. Similarly, G1 will be G1 of the first sequence, G1 of the second, G1 of the third, G1 of the fourth, and so on. So you have to write it down in this way: 1 0 1 1. That's your G0. Let's do that. G0 is 1011. G1 is, it's easier if I write them down. One below the other. 0010. G2 is 0011. G3 is 1100. And G4 is 0101. Okay, and then you write down your matrix. So 1011, 0010, 0011, 1100, 0101. Then you stagger it. So start from here: 1011, 0010, 0011, 1100, and 0101, and so on. So that's your generator matrix. So these numbers will be different in your assignment question, but the method is the same. And once you have your generator matrix, we can check with the options given and mark the right option. Okay. The fifth question. Are they using the same thing again? Let's see. So they're using the generator sequence from the previous question. So since our generator sequence itself is different, I modified that. I'll use the same information sequence. Okay, so the code word sequence corresponding to the information sequence u is equal to 1011 is initially the encoder is in all one state. So here the state will be the memory elements, value of the memory elements, and the memory elements in our question is ul minus 1, ul minus 2, ul minus 3, and ul minus 4. Ul is the input at time L. So initial state S is all ones, so it will be 1111. Yes, is there a problem? I heard some sound. Did someone raise your hand or something? I guess not. Okay. To make this question simpler, so you will, okay, you can make a table. I won't draw the table exactly. I mean, I won't draw grid and all, but consider this a table. You have ul minus 1, ul minus 2, ul minus 3, and ul minus 4. You have vl1, vl2, vl3, and vl4. So initial state you have 1 1 1 1, and your input, so your input u is 1 0 1 1. So you're sending 1 this bit first, right? And what happens, you have a register like this. You have 4 memory elements, 4 registers, 4 flip flops, and once you push an input here, this last input will be discarded, and this one will be pushed to the first place. One in the first place will be pushed to the second place, one here will be pushed here, finally this third one will be pushed to the final place. So your new state will be 1 1 1 1. Suppose your input was 0, then your 0 would come to the first place, then each of these would get shifted by one place, so you would get 0 triple 1, and the final one is discarded. So here the next state would be, since your input was a 1, it will still be 1 1 1 1. Okay, so at the time L, you have the values of ul minus 1 up to ul minus 4. So using the equations for v, let me copy the entire thing. You can fill up the values for each of the VLs. So VL1 is UL plus UL minus 3. So it's, so now at this point all of UL to UL minus 4 is 1, so you are just adding ones everywhere. So VL1 is 1 plus 1, just 0 in mod 2. UL2, VL2 will be UL minus 3 plus UL minus 4, which is 1 plus 1, that's also 0. There are 3 terms in VL3, so each of those is 1, so we'll get a 1. And then 3 terms is in VL4, so each of those is 1 at this point, so we'll get a 1. So the initial output sequence at time L is 0 0 1 1, right? So if you write out the output, it will be 0 0 1 1. Of course you have to interleave, but I'm not bothering about this. The answer in this is in this form, I think, so we'll leave it at that. And then next state, so this one was pushed here, this one was discarded. Now your new state is 1 1 1 1. Your new input is the second bit, so now you're pushing in 0. That's your input. Again, write down the outputs. UL plus UL minus 3, 0 plus 1, which is 1. UL minus 3 plus UL minus 4, 1 plus 1, which is 0. UL plus UL minus 1 plus UL minus 2, 0 plus 1 plus 1, which is 0. And ul plus ul minus 2 plus ul minus 4, 0 plus 1, which is also 0. So your output is 1000, and the contents of your register will change to 0111. So this 0 will come here, this 1 is discarded. So 1000 was your output. We'll do the next input, which is 1. So the next input is 1. Now the output VL1 is UL plus UL minus 3, 1 plus 1, 0. VL2 is UL minus 3 plus UL minus 4, 1 plus 1, which is also 0. Then UL plus UL minus 1 plus UL minus 2, this is 1 plus 0 plus 1, which is also 0. And finally, that's 1 plus 1 plus 1. Right, so the next output sequence is 0 0 0 1. Finally, okay, now since 1 was the input, that will be shifted into a register in the next step. So we'll get 1, and this 0 will go here, I will get 0 1 1, and this 1 is discarded. So at this point your shift register content is 1011, and your final input is this bit, which is 1. And the final output sequence UL plus UL minus 3, 0. UL minus 3 plus UL minus 4, 0. Sum of the first 3 bits, which is again 0. And UL plus UL minus 2 plus UL minus 4, that's also 0. So you get 0 0 0 0. So for the information sequence 1011, our convolutional code will give out these 4 output sequences: 0011, 1000, 0001, and 4 zeros. You can follow the same procedure for the assignment question. You will get different answers because they have a different generator. Okay, we are halfway through, so I'll take a 1 minute break and I'll be back. Alright, I'm back. Let's go to question number 6. So they are saying 6 to 9 will use the same convolutional code. I'll change it a little bit. Let's see. Well, let me write the question first. Consider a non-systematic feed forward convolution encoder whose block diagram is given below. Use the same block diagram for Q6 to Q9. For question 6 is what is the state diagram of the code? Now if I use the same block diagram, then you will get the answers for your assignment questions. So I have to change it a little bit, which will change all the answers. Hopefully nothing goes wrong. What should I change it to? How about I use the VLs from the previous question? I'll cut it down to only 3 of the output with only 2 memory elements. Well, if I only use 2 memory elements, there are only so many code generators that I can use. And they've already used all the nice ones in your question. Okay, I'll only do a small modification. There aren't that many meaningful questions I can form with these small parameters. And if I increase the memory, there will be too many states, and everything will be a mess. So I'll just do a small change. Let me say, instead of a non-systematic encoder, I'll just use a systematic feed-forward encoder. And let me have my VL of 1 should to be equal to just UL. VL of 2 is UL plus UL minus 1. And VL of 3 is UL plus UL minus 1 plus UL minus 2. I don't know how this is going to turn out, but let's see. So that would mean my block diagram is I just have a UL coming out here. That's UL. Yeah, you have UL minus 1 stored there, and UL minus 2. So your second output will be sum of UL and UL minus 1. So let's let that be VL2. Okay, there you have your VL1, VL2, and VL3. So VL1 is UL, VL2 is UL plus UL minus 1, and VL3 is UL plus UL minus 1 plus UL minus 2. Okay, now we have to write the state diagram. For that, since there are two memory elements, you're storing UL minus 1 and UL minus 2. The value stored there will give you the state. So your current state, that is the value stored in UL minus 1 and UL minus 2. You have your input here, which is UL. The next state is, let's say it's UL minus 1 prime and UL minus 2 prime, which will be equal to, so the UL gets pushed into your input, it gets pushed into the first register, and the content in the first register is pushed into the second flip-flop. Okay, and then you have your output VL1, VL2, VL3. So VL1 will be just your UL, VL2 will be the sum of the first two bits, VL3 will be the sum of these three bits. So to write down the state diagram, first you can have four different states with two memory elements. You are in either state 0 0, can be in state 0 1, you can be in state 1 0, or in 1 1. And when you are in each of these states, you might get an input of 0 or 1. So your input might be 0 or 1. And depending on your input, your next state will change. So when you're in state 0 0, if your input is 0, you will be in state 0 0. If your input is 1, you will go to state 1 0. If you're in state 0 1 and your input is 0, you'll go to 0 0. If your input is 1, you'll go to 1 0 again. So in state 1 0, if you get a 0, you'll go to 0 1. If you get a 1, you'll go to 1 1. And in state 1 1, if you get a 0, you'll go to state 0 1. And if you get a 1, you'll go to state 1 1. So those will give you the state transitions, right? From that you can write, first you can write the transitions. So in this case, right, where you have two memory elements and only one input, the transitions that happen will be the same regardless of the equations for your outputs. So regardless of the input output equations, the same transitions will happen, and they will happen for the same inputs, right? So this next state doesn't depend on your generator, doesn't depend on your code. So if you only have 1 bit input and 2 bit storage, then this will always be the state transitions. Only thing is, on the edges of those transitions, you'll get different outputs for different convolutional codes. So the structure of the state diagram will be same for all questions of this type. So 0 0 can either stay in 0 0 or go to 1 0. 1 0 can go to 1 1, or it can go to 0 1. Similarly, 0 1 can either go to 1 0 or to 0 0. 1 1 can go to 0 1, or it can stay in the same state 1. So that's it. That is the structure of your state transition diagram, and the state transitions will happen for these particular values of your input. That is also the same. Now we have to fill in the outputs in each of those transitions. So let's see the outputs. A VL is nothing but UL, so it will simply follow, it will simply be the same as this. So I can just copy that down and paste it for VL. Alright. UL is the sum of VL2 is the sum of UL and UL minus 1. So it's the sum of these two. So it will be 0 1 0 1 1 0 1 0. VL3 is the sum of all three bits. So it will be 0 1 1 0 1 0 0 1. So from state 0 0, when you transition to 0 0, the output is 0 0 0. So this is 0 0 0. And that will be true for all convolutional codes, because your VL output will be a function of your ULs, and you started out with an input 0 and memory state 0, so you will only get a 0 output. Next 0 0 will go to 1 0, having an output of 1 1 1. 0 1 2 0 0. So this one has an output of 0 0 1. So this is the change. This is different from your assignment question. So by changing the generator, I change the output value on the edges. Next 0 1 to 1 0, you have the output 1 1 0. 1 1 0. 1 0 to 0 1, you have 0 1 1. 1 0 to 1 1, you have 1 0 0. 1 1 to 0 1, you have 0 1 0, and 1 1 to 1 1, you have 1 0 1. So this is the state diagram for your convolutional code. That's what they asked in question 6. So we are done with question 6. That's the answer. Okay, the next question. So using the same state diagram, the weight enumerating function of the code is, so this loop here, you will remove that and write down your state 0 0 0 as your initial and final state, and then from 0 0 you go to 1 0. From 1 0 you can either go to 0 1, or you can go to state 1 1. From 1 1 you can go to 0 1, or you can stay in that state itself. From 0 1 you can go to 0 0, or you can go to the state 1 0. Now you have to put weights on these edges. So the way you put the weights is, when you go from 0 0 to the state 1 0, your output is 1 1 1. The weight of that output sequence, so by weight we mean Hamming weight, the number of ones in it. So there are 3 ones, so the weight is 3, but we write that as the power of our variable x. So we write this edge as x3. So the exponent of x is the weight of the code word on that edge. So this will depend on your output sequence. So if you have a different generational convolutional code with a different generator matrix, then the structure of this map will be the same, this diagram, right? You'll have the same states with the same transitions. Only difference will be the power of x's on each of the branch. 1 0 to 0 1, you have the output 0 1 1, that has two ones, so this is x squared. 1 0 to 1 1 is 1 0 0, so that is an x, it has a single one. 1 1 to 1 1, that is x squared. 0 1 to 0 0 0 0 1 has a single one, so that branch has an X. 1 1 to 0 1, 0 1 0, which has a single one, so that is an X. Finally 0 1 to 1 0, 1 1 0, which has two ones, so the weight is 2. So this branch also has a weight of 2. So this is what you should write down first, the modified state diagram, when you want to find the enumerating function. That's the first step. Next step, you find out the number of loops. Of course, since the structure is the same for this type of problem, the number of loops and everything else will be the same. So there are three loops. Three loops. First loop is so from 1 1 to 1 1, and the gain on that loop is x squared. Next loop is 1 0 to 1 1 to 0 1 to 1 0. So this loop, the gain on that path is x, x and x squared. So it is x power 4. Sorry. So this is a forward path, not a backward path. So the actual loop is uh, this one. So the weights are x, x and still x square. So the weight is still x power 4. Final loop is this loop, which has x square going forward and x square coming back. So the final loop is 1 0 to 0 1 to 1 0 again. So you get a gain of x power 4 once again. Next you see pairs of non-touching loops. So there's only one pair of non-touching loops, and that pair is this loop and this loop. So two loops are non-touching if they don't have any state in common. If you see this loop and this loop, those have this state 1 1 as common. If you check this loop and this loop, they have state 1 0 and 0 1 as common. So only the loop there and this loop here have no common states. So you multiply the gains of those loops and write them down. So that is C1 and C3, which is x square into x power 4, which is x power 6. Now your delta, the denominator of your transfer function, x is 1 minus summation of the gains along single loops. So C1 plus C2 plus C3, the x square plus x power 4 plus x power 4 plus the summation of products of the gains of non-touching loops. Here there's only one pair of non-touching loops, so there's no summation. It's just C1 C3. So it's just x power 6. That gives the denominator of your weight enumerating function. Now for the numerator, there are two forward paths you can take. First forward path is straight here. I'll call that the first forward path. Second forward path is going here and going here. That's the second forward path. So for the first forward path, the gain will be f1, and the path is from 0 0 you go to 1 0, 0 1, and then go to 0 0. So the gain along those is x cube, x square, and x, which will give you x power 6. F1 is x power 6. The second forward path is from 0 0 you go to 1 0, then you go up to 1 1, then you come back down to 0 1, then you go to 0 0, and the gain along that path is x cube, so x cube, and then you come across x, so that becomes x power 4, then one more x, that's x power 5, and one more x, that's x power 6. So gain along the forward path 2 is x power 6 again, and the value of delta in each of these paths, delta 1. To get the value of delta 1, you have to remove all the nodes in that path. All the, by nodes I mean the states. So first path is here, so you have to remove the first 4 states. You will be left with only state 1 1, and you have to use the same formula, 1 minus sum of the loop gains plus sum of the product of the loop gains of non-touching loops, and so on. But if you have only one state, 1 1, which has only one loop with a gain of x squared, so this will become 1 minus x squared. So your delta 1 is 1 minus x squared. Similarly, you do for delta 2, you remove the nodes along that forward path, and you find that the forward part 2 goes through all of the states. So when you remove all of the states, nothing is left. So in this loop formula, for the value of delta, there are no loops, so all these terms will go away. You will be left with 1. So delta 2 is 1. Then finally you write out t of x is summation fi xi by delta, fi delta I by delta. So it's f1 delta 1 plus f2 delta 2 by delta, which is f1 and f2 both are x power 6, x power 6 into 1 minus x square plus x power 6 divided by, oh I never got around to writing this. What is this? This is 1 minus 2x power, okay, 1 minus x square minus 2x power 4 plus x power 6. So 1 minus x square minus 2x power 4 plus x power 6, which will be 2 times x power 6 minus x power 8 divided by 1 minus x square minus 2x power 4 plus x power 6. Okay, so that's the weight enumerating function. We'll go to question 8. Same question, same diagram. Free distance of the code is, so you can directly look at the least value of the power of x in the numerator, that is x power 6. So the answer is 6. There's a code word of length 6, code sequence of length 6, of, sorry, not length 6, weight 6. So that will be your minimum distance or free distance in this case. But a small thing I wanted to tell you is you have t of x, which is equal to 2x power 6 minus x power 8 divided by 1 minus x power x square minus 2x power 4 plus x power 6. If you had something like 1 plus sorry, if you had something like x power x square plus x cube plus etc., then obviously that means there is a code word of uh, weight 2 and a code word of weight 3. So the free distance is the minimum weight, which is 2. But there's this denominator term. So what to do with that denominator? What you do is you treat it like a normal variable you treat in other algebra classes, and you write this as a 1 minus x square minus 2x power 4 plus x power 6 to the power minus 1. And you, just for convenience, let me write minus x square minus 2x power 4 plus x power 6 as some variable x prime. So t of x is 2x power 6 minus x power 8 into 1 minus 1 plus x inverse. So you can use the Taylor expansion or whatever expansion it is and write this as 1 minus x is x square is x cube etc., an infinite sequence. So since you have this 1 here and these are all some other powers of x, which would mean that when, okay, this was x prime, so x prime square, whatever you do with this, you will get higher powers of x. So they will all have power of x greater than 1. X, you can think of 1 as x power 0. So when you multiply this out, the lowest power term for x you will get is 2x power 6 into 1. So you'll get something like that, minus x power 8 minus 2x power 6 into x prime, which will be a higher order term. So that's why you can be sure that if there is a 1 in the, since there is a 1 in the denominator, you can always do this Taylor expansion. Uh, Actually, I don't remember. Is it? Yeah, this is the Taylor expansion, right? Whatever expansion this is, you can do that, and you will end up with the least power being the least power in the numerator. Okay. So that's the same type of thing they do in your generator matrices also. So in your lecture, maybe you might have been confused where they say that uh, 1 over 1 plus d is an infinite weight information sequence, and they write this as 1 plus d square, etc. So it goes on up to infinity. So the information sequence, you are using infinite number of bits. So in time domain, this will be ul plus ul minus 1 plus ul minus 2, right? So the way they write this is also the same thing. They're using this is a geometric progression with the common ratio d. So they are using sum of the geometric series is a over 1 minus r. But this is mod 2 arithmetic. So there's no minus 1 is equal to plus 1 in mod 2 arithmetic. So this will turn to a over 1 plus. So here a is 1 and r is d. So it should be 1 over 1 minus d, which is nothing but 1 over 1 plus d. So even though this d and x and all are actually not exactly variables, you can treat them as normal variables. Okay, that's question 8. Question 9: is the encoder catastrophic? So to find out whether is the encoder catastrophic, and the answer, the way you find out is, so the code is catastrophic if there exists a loop in the state diagram that has a zero output weight for a non-zero input weight. That means here, since you are giving only one bit, if your bit is 1 but your output is 000, then your encoder is catastrophic. So here there are only two loops. For the 000 loop, you are giving input 0, so it's fine. For the 1 1 loop, you are giving input 1, but you are not getting a 000 output, so this encoder is not catastrophic. One more thing I wanted to tell you is catastrophic codes may have equivalent codes that are not catastrophic. And I'll give you an example. You take g of d is 1 plus d square 1 plus d. This will be catastrophic. And an equivalent code for that is g prime of d should be 1 plus d, and 1 is not catastrophic. So as an exercise, you can write the state diagrams of both of these. So this first one has a d square element. There will be two memory elements, ul minus 1 and ul minus 2, but this has only one memory element, so there will be only two states. So the state diagrams will be different. You can write down the state diagrams and the state transitions for both of them and check. Even though they are equivalent codes, one of them is catastrophic and one of them is not. Okay, we'll do the final question and leave. I guess I'll change this question as follows. Write the generator matrix in transform domain given the following IO relationships, and I'll use the relationships that we had in the previous question. I'll use the same thing and write down the transform domain matrix. So first thing you notice is, so your code sequence VL1, VL2, VL3, VL4 will be a product of your state and the input and the generator matrix. So this will be UL minus 1, UL minus 2, UL minus 3, UL minus 4 into G of D. So this is 1 by 4 and this is 1 by 5. So this will be a 5 by 4 matrix. And you write down the matrix from the relation. You have U into. So the first one will be the dot product of first code sequence output will be the dot product of the information sequence and the first column of G of D. So wherever there's a 1 coefficient here, there will be a 1 in the corresponding row in G of D. Wherever there's a 0, there will be a 0 in that corresponding position in your matrix. So since the VL of 1 is nothing but UL plus UL minus 3, you can write UL 0 times UL minus 1, 0 times UL minus 2 plus UL minus 3 plus 0 times UL minus 4. So there will be 4 columns like that. Second column UL minus 3 and UL minus 4. So it will be 0 0 0 1 1. Uh, Sorry, just one difference here. So eh, sorry, that's not how you write in the transform domain. That's how you write in the, sorry for the mistake there. So you are writing it in the transform domain. So you just have one input here. So it's a bit different from your assignment question. There are two inputs, so there will be two rows. If you have one input, so it will just be one row, right? UL times, it's UL plus UL minus 3. So you multiply this by 1 plus D cube. So what will happen? The first element VL1 will be ul times 1 plus d cube, which will be ul plus d cube ul. So in the time domain, this will transform to, since ul is doesn't have a d cube operating on it, it's, you can take that as d power 0. So you'll get ul in the time domain as it is, and then since you're multiplying ul by a d cube, that means in time domain you are delaying it by 3, so you'll get ul minus 3. Okay, so this will be ul minus 3 plus ul minus 4, so ul is delayed by 3 and 4, so this will be d cube plus d power 4. The next one will be ul plus ul minus 1 plus ul minus 2, so you'll have 1 plus d plus d square. Finally ul plus ul minus 2 plus ul minus 4, 1 plus d square plus d power 4. So that's how you write the generator matrix in the transform domain. Let me just give a small example, right, and then we'll finish it off, finish this session off. What if you had two inputs like you have in your assignment? I'll just change it up a bit. Let's say you have ul1, vl1 is ul minus 1, ul minus of the second input. So there are two inputs here. First input is labeled by superscript 1 and second input bit is labeled by superscript 2. Let's say the third one is ul minus 2 plus ul of the second one. So in this case, the transform domain matrix will be vl1, vl0, vl1, vl2 is the product of, so there are two information bits here, ul1 and ul2. So there will be two rows. So vl0 is simply sum of ul which is not delayed, so 1, and when you take the, so the first one will be in this case the dot product of this and the first column. Here since you had only ul, the dot product is just the product of these two terms. Okay, so you are taking 0 times ul. Next vl1 is ul minus 1 of the first input and ul minus 1 of the second input, so both of them are getting delayed. So ul minus 1 you have to delay it, so you multiply by d, and ul2 you have to delay it, so you multiply by d. Finally vl2 you have ul minus 2 of the first input, so you have to delay by 2, and you are using the second input as it is, so no delay for that. So that is how you do if there are two inputs. Okay, that's all for today's problem solving session. I hope that was helpful.